Great. Hi, everyone. I'm Stephen Schmidt. I am a fourth-year PhD student at Johns Hopkins University, and today I will be talking to you about how, for the first time, I have time-resolved the formation of giant planets outside the solar system. So to begin with, come on now. Okay. To start out, we need some context, so let's talk about the solar system. So specifically, the NEAS model and its updated versions have modeled the formation of the solar system such that somewhere between tens to hundreds of millions of years after the dissipation of the parent protoplanetary disk, a dynamical instability causes the giant planets in the solar system to undergo migration. This leaves some observable predictions, like the existence of Jupiter's Trojan asteroids. Now, we previously haven't been able to time resolve anything like this outside of the solar system beyond like this protoplanetary disk phase of planet formation. But now, for the first time, as I'm about to show, we have evidence for the time-resolved, longer-scale evolution of hot Jupiter systems. Now, hot Jupiters are this region that I'm highlighting here. They are giant planets that orbit very close to their host stars, in stark contrast with our own solar system. Now, we have a few theories about how these planets can form. And we generally categorize them into three different mechanisms. We've got disk migration or in situ formation, where the planet forms close to its host star or migrates inward through the parent protoplanetary disk. We've got high centricity migration, where some dynamical instability far away from the host star causes it to have a high centricity and then circularize over time. And then tidal inspiral, which causes the planet's orbit to lose angular momentum and move it inwards and therefore disrupt it or destroy it. Now, each of these different mechanisms have different predictions for the times at which they occur in red, as well as the orbital period distributions that they tend to produce. And so we can look at the orbital period distribution of hot Jupiters that we've observed, and we can see that we have several features, like a peak in the distribution between 3 and 4 days, as well as several planets both closer in and further away. And so thinking again about these different mechanisms for hot Jupiter formation, the combinations of these physical processes I've described could lead to different typical population level ages of planets near the peak, in the middle, interior to or inside the peak, and ones outside the peak. And so in particular, this one on the right here, if we have a combination of some early time uniformly-ish distributing mechanism and then this late time peak populating mechanism, plus efficient tidal inspiral, could result in subpopulations near and inside the peak being a bit older than the ones outside the peak. So let's test this. Going back to the hot Jupiter period distribution, we want to isolate the peak of the period distribution, but we have this problem with a bias incurred by the transit technique, which most hot Jupiters have been discovered by, where the probability to observe a transit of a hot Jupiter decreases as it gets further away. So to correct for this, we use these systems' known scaled semi-major axes, the inverse of this thing on the right, and we debias the peak of the period distribution, which we can therefore then split the hot Jupiter population into subpopulations near the peak, inside the peak, and outside the peak. Now, thinking about ages, it's difficult to determine the ages for exoplanet host stars that are mature, older than like 1 billion years. So a way around it is the population level velocity dispersion method. The way this works is that planets in our galaxy, or stars in our galaxy, form pretty close to the galactic midplane, and they experience random kicks that excite their velocities. And if you take the standard error of a distribution of velocities for a given population of stars, you can see that this is a monotonically increasing function of age. So you can see this in action with the age-velocity dispersion relation for the solar neighborhood. As you go older, you can see that with increased age, you get increased velocity dispersion. What we can do is then find the intersection between a given exoplanet host star population and this age-velocity dispersion relation, and with that intersection, calculate its characteristic mean age for that population. Now, zooming in a bit for hot Jupiters, because they're a bit young, we find that the subpopulation near the peak is around 3 million years. Similar sort of deal with the subpopulation inside the peak. It's a little bit older than those. But we also find the subpopulation of hot Jupiters outside the peak are considerably younger. So this would point to this fourth scenario that I've highlighted here and described earlier, best matching our results. But we can go further. what I did is I created a parametric forward model to understand and model the formation and overall population of hot Jupiters in an attempt to replicate this, the observed period distribution in ages, specifically the ages, or what we're interested in, of this hot Jupiter population. So the main thing that we want to get from this is the time lag between these early mechanisms and this late mechanism that could cause hot Jupiters to form. And so the way that I'm going to visualize what my results are for this are through this triangular plot that shows how the combinations of different mechanisms may or may not be consistent with our observations. So to understand what's going on here, this x-axis is showing the late time peak populating fraction, like approximately highest centricity migration at late times. This y-axis is showing an early time peak populating mechanism, so something at earlier times. And because we have three different mechanisms, each of these different corners of this triangle show a hot Jupiter population that is formed almost entirely by that mechanism. So in addition to this, we've also got two different tuning parameters up here. We have the time lag in gigayears between the formation of the planetary system and that late time mechanism, as well as Q star, the stellar tidal quality factor that tells us how efficient tidal dissipation is in the system. So for high values of Q star, there's not a lot of tidal dissipation, and for low values, there's a lot. So additionally, we have different colors of points, and we're also going to show ranges of colors here to kind of show the regions where it's consistent in yellow and green. Specifically, yellow shows qualitative consistency, green shows quantitative consistency with those ages that I showed earlier, and then red shows population combinations that are not consistent. So with this in mind, let's get to our results. For high values of Q star, so like 10 to the 8th, you need very little tidal dissipation. So with that, we don't see a lot of consistency. So this suggests that we need some tidal dissipation in our population to get the ages that we observe. However, if we go down to smaller values of Q star, we end up finding a similar deal, which means that we can't have too little, which is a reasonable thing. If we go to a middling value, we start to get somewhere with a moderate value of Q star, but we're still getting only qualitatively consistent results with low time lags of 1 gigayear or less. But when we go to a time lag of 1.5 gigayears or more, we are able to see a region where a majority of the hot Jupiters in this scenario have formed via this late time mechanism. Now this means that there are some hot Jupiters that form via this uniform or whatever early time mechanism that results in it being like, a lot of those are outside of the peak. So in summary, we have for the first time resolved giant planet formation outside the solar system. We find from this that most hot Jupiters are late arrivals, typically taking 1.5 gigayears or more to arrive at their observed locations. And with this, a lot of hot Jupiters that orbit with orbital periods beyond 5 days may have formed in some different mechanism than the ones near the peak, which could be interesting for other applications to the solar system, to atmospheres, etc. Thank you, and I'll take any questions.
We have good time for questions.
Hi, Ilaria Pascucci, University of Arizona. So can you comment on the mechanism for having these late arrivals? Does it require other giant planets in the system? Or?
So the way that we modeled it was via planet-planet scattering. Theoretically, it could also have things like Kozai late oscillations, excuse me, or something like that. We tried to be as agnostic as possible to the specific mechanism, other than the fact that it occurs at late times and tends to populate the peak via something like high centricity migration. But in general, we assume planet-planet scattering is like the main thing that's causing it.
Hello. Hey, thank you. That was a very nice talk. So, this is Bryce Boland from Eureka Scientific. So, my question for you is, do you assume a smooth or kind of a grainy or like a stochastic migration for these hot Jupiters, or what exactly are your assumptions for the migration?
So we don't get too fine-grained in terms of how this formation happens. Generally, we kind of assume, okay, the hot Jupiter arrives at a particular location. We don't really want to go too much into detail with that because that could that leads to a lot of assumptions about it. But what we do is we assume for high centricity migration that it starts further out and then it like basically circularizes to a orbital period that would be in the peak of the hot Jupiter orbital period distribution.
Very good. Thank you. Thank you very much.
Thanks.
Last talk of the session is